Okay, so today we are diving into a landmark paper, one that fundamentally changed how computers see the world. It's called SSD, which stands for Single Shot MultiBox Detector. To really get why SSD was such a big deal, you have to understand what things were like back in, say, 2015. In the world of object detection, you were basically stuck with this really frustrating choice. You had two main camps, and neither was perfect.
On one side of the ring, you had these heavyweights like faster RCNN, and they were incredibly accurate. I mean, look at that MAP score. That's just a way we measure precision. It's really high, but the speed? A measly 7 frames per second. That's a non-starter for anything real-time. Then in the other corner, you had speed demons like YOLO, blazing fast at 45 FPS, which is great, but you paid for it with a big hit to accuracy. So the choice was simple but awful. Fast or accurate. You couldn't get both.
And this was the dilemma, the big problem everyone was trying to solve. See, the really accurate methods, the slow ones, all use this two-step dance. Step 1, the network would propose a bunch of regions, basically saying, hey, an object might be here, or here, or here. And then step 2, another part of the network would go back and classify each of those proposed boxes. It worked, sure, but it was a massive computational bottleneck, just too slow.
But then, a new paper came along, and it asked this super simple but totally revolutionary question. What if you could just do it all in one go? What if you could just get rid of that whole region proposal step and find everything in a single pass? And that, right there, is where SSD enters the story. It came in with this brand new unified framework that packed all the computation, everything you need for detection, into one single elegant network.
So the key idea, the whole magic trick, is this concept of a single-shot detector, right? Instead of one network guessing the boxes and a second one checking its homework, SSD does it all at once. That single pass, that's what made it so unbelievably efficient.
So how'd they pull this off? Well, the paper introduced 3 really clever innovations. First, they used these small, super-efficient convolutional filters to predict both the object's category and its location at the same time. Second, and this one is the real genius move, it made these predictions on feature maps at different scales. And third, it used a set of predefined default boxes, think of them as starting templates, of all different shapes and sizes. This gave the model a huge head start on getting the predictions right.
Okay, let's talk about that multi-scale thing, because that was the real secret sauce. This was the key that unlocked how to get super high accuracy without needing that clunky, slow, two-step process.
I mean, the authors of the paper said it perfectly. They figured out that as you go deeper into a neural network, the different layers naturally start to see the image at different scales. So they thought, hey, why don't we just take advantage of that? Let's use the outputs from all these different layers to make our predictions all at the same time.
Here's a great way to think about it. Imagine you're looking at a picture with a wide-angle lens. You can see the whole scene, right? It's easy to spot the big stuff. Well, that's kind of like the later layers of the network, the coarser feature maps. They're fantastic for spotting large objects, like the dog in this classic example from the paper.
Okay, now imagine you switch to a zoom lens. You're zeroing in on the details, and now you can spot the small objects you might have missed before. That's exactly what the earlier, finer feature maps in the network are doing. They're perfect for finding smaller things, like the cat. And what SSD did so brilliantly was combine the wide-angle view and the zoom view all at once.
So, you put all these innovations together, and what do you get? Well, SSD didn't just break that old trade-off between speed and accuracy, it completely shattered it. Just look at this. The main SSD model, the SSD 300, clocked in at an unbelievable 59 frames per second, and this is on the high-end GPUs of the time. That isn't just fast, that is truly real-time performance. But you know the big question, was it accurate? And the answer is a resounding yes. Here's the proof in the pudding. Look at this comparison. SSD wasn't just faster than YOLO, it was actually more accurate. And get this, it wasn't just more accurate than the super precise faster RCNN, it was more than 8 times faster. It won on both fronts. No more compromise. Let's look at the hard numbers, straight from the paper's own benchmarks. That 74.3 MAP score, that officially beat faster RCN at its own game. And that 59 FPS, that wasn't even in the same ballpark. It was a completely different league. So, for the very first time, developers had a model that gave them the best of both worlds. This was an absolute game changer.
So why are we still talking about a paper from 2015? I mean, in AI, that's ancient history, right? Well, because its core ideas, they're absolutely everywhere now.
That whole idea of an efficient, single-shot, multi-scale detector, it's not just an idea anymore. It's a foundational building block for so much of modern computer vision. This is the technology that truly unlocked real-time AI. It's what paved the way for things we see all the time, from self-driving cars detecting pedestrians, to the live camera filters on your phone, to high-speed robots on assembly lines, and even helping doctors spot anomalies in medical scans.
And really, that's the paper's biggest legacy. It showed the entire field a new path forward. It proved you don't have to choose between speed and accuracy, and in doing so, it completely changed the question researchers were asking. It went from how do we make detection more accurate to how do we make accurate detection incredibly fast? And that's the question that's still pushing innovation today.
This is for entertainment purposes only.